All right, we are deep in the heart of this calculation, and I just was noting here that, so maybe I'll just point out, just to make it perfectly clear, that sorry, that was a little strange, x transpose equals xi is the matrix where the ijth entry is xi times xj, where x is this vector x1 up to xd. So that means that this is, this trace is a nice dot product between these sort of functions of x. Okay, so hopefully that was clear why that looks nice. And now we have, what else do we have? We have this part, and this is 2 minus cancels. Actually, the 2 cancels. We get the sum over k, I'll just leave the k off, of zk. So now let's pull together the zk and the x once again. So we get zk x transpose. We can transpose this. This is a scalar quantity equal to its transpose. And lambda k is always symmetric because a covariance matrix is symmetric and the inverse of a symmetric matrix is symmetric. All right, so with that, that's that one. And that's also looking good because that's clearly a dot product here of this thing. This is zkx with this parameter stuff. And then what do we have left? Oh, we should have also put beta, should have also included, right, we're going to have a zk over here. So let's modify the definition of beta k. This should also have a minus, what should it be? Minus 1/2 mu k transpose lambda k mu k, because that's going to go with zk up here. And all this stuff, the betas are just functions of the parameters. So that's a nice dot product there. Z with beta. This is a nice dot product, and this is a nice dot product. So I think we're looking pretty good for an exponential family. And we can go ahead and read off now. We can just read off what are the sufficient statistics. So the first sufficient statistic, or the first set of sufficient statistics, is the vector z. That's this part. So the sufficient statistics, let's scroll down. So the sufficient statistics are z, or all the elements of z. And then we're going to have zk x transpose, or that's a matrix, but all the elements of that are included among the sufficient statistics. So the sufficient statistics are going to be all of these things sort of combined, all together. And this is for each k from 1 to m, all combined. And then, so that's a bunch of matrices there. And then we have zk x transpose, or just x, same thing, for all these k. And so these all together are our sufficient statistics for this distribution. And now that we have this, so let's so back up a minute. Now that we sort of got to this point, figure out where we are. So we were thinking about, so we wanted to get, we wanted to be able to evaluate this expression here to solve for theta as prescribed by our EM algorithm. And in order to do that, we needed to first figure out what the sufficient statistics were. And to start to figure out what the sufficient statistics were, we first wrote down the probability here of the joint thing for the case of a single x and z, just a single observation of x and z, or single, instance. But now we're going to have multiple instances. So the problem that we're considering, if you think about this problem, we're going to get a bunch of examples, right? We're going to get a bunch of samples from this distribution, and each of those has an x and a z. So the joint, so the x that we need to think about is actually a vector, not a vector, but it's a sequence of x's, and each of them is a vector. So we actually need to write this down. We need to write down this distribution in the case of several IID. We'll assume that they're IID. That's, of course, an assumption that we'll make, part of our model. We'll assume that they're IID draws from this distribution, and we'll write down, so let's do that. Let's write down that. When they're IID, so now it's multiple, the probability of all of these, let's say there's n of them, x's and z's, the complete likelihood, as they say, and this depends on theta. Did I put theta here? That's theta. Is the product. It's the product as I goes from 1 to n, just by independence. And now each of these xi's, so this is sort of different notation here. Now each of these xi's is a vector. Xi is a vector. Xi1 up to Xid. And z is a vector, or zi is a vector. Zi1 up to Zim. And each of these factors is just this thing right here. But we're going to put zik instead of zk, and we'll put xi instead of x. So what is that going to be? So that's going to be, I'll see if I can squeeze this in here. So when we take the product, we're going to take this, it'll be the sum in the exponent. So this is e to the sum. These were each sums over k. Sorry, I'm trying to keep both sort of on the screen, but you can only see half of this one. This is the sum. Maybe I'll scoot it up a little bit so you can actually see them both. Okay, maybe that's a little better. So this is the sum now. That was k, k, and k. Now we also have a sum over I. So we're going to have, let's go ahead and move that in. So we have k, and now we have the sum over I, zik, beta k, minus 1/2, sum over k. The sum over I traces linear operation, so the sum over I moves through here, and we get the trace, sum over I, zik, xi transpose, times lambda k. Multiplication of matrices is linear. Oh wait, that should be trace. I want to pull that together, and then that's the trace of this product. Okay. And then we get one more here, sum over k. And now the only stuff that depends on I is this zik and xi. So let's do that, and that's the sum over k, lambda k, mu k. Whew! Barely fit on the line. All right, so that's our expression here for this thing. And now, once again, we can just read off the sufficient statistics. So the sufficient statistics this time, now they are the sufficient statistics for this distribution. This is also an exponential family, but it's an exponential family over all of these random variables. And the sufficient statistics are just these guys right here. It's the sum of I over I of zik, the sum over I of zik times xi transpose, and the sum over I of zik xi. So these are sufficient statistics. And now that we got our hands on the sufficient statistics for EM, so now we're in good shape. But let's go back here to what we wanted to do. This is the thing for EM. So now we've got our hands on these sufficient statistics. And here now for the product, when we have multiple instances, this x and z should be interpreted as the sequence of x's, x1, x2 up to xn, and the z should be interpreted as the sequence of z's, z1, z2, and so on up to n. So now let's write down what this formula is. So this is for each I. This is for each. Maybe I should put, maybe to distinguish, I was using I below for the data points. We could say j here for the different sufficient statistics, and this is for each j, however many sufficient, however many elements there are in the sufficient statistics. Okay, so let's write down these expressions for the actual sufficient statistics that we found. So we're going to have, and we can actually lump them together. So this is for each j, each coordinate. All of these equations are to hold simultaneously. And so we can group them, we can break them up into groups. And so I'm going to do that. I'm going to break them up into these natural groups that we found here. And the first one, let's do this one first. This one, so this is the first one. The expected value under theta 0, the conditional expectation of the sum, just this function here, this sufficient part of the sufficient statistics, given that x equals little x. And here x, I'm using x or little x to be this sequence of observations, x1 up to xn. And I'm going to use z for the sequence of z's, z1 up to zn. And each of these is a vector, right? That was this. Each of these is one of these vectors. Okay. So we need to have this equal to, this conditional expectation equal to the expectation under just theta alone of the same thing. Sum over I, z, I, k, that's a random variable z, I, k, this is also random z, that should be clear, I think, from the context. And let's solve this. Now we want to solve the next, so that we formed that expression, and we're assuming that this theta naught is known. That's the theta from the previous step of EM. And now to get the theta for this step of EM, the next theta, we need to solve for theta here. So let's see if we can do that. This is the sum. Expectation moves through zik. And what is zik? Let's go back. Let's remember what the definition back up here in our Gaussian mixture model. Think about to get the expected value of zik. Zik is the kth coordinate of a vector zi that's distributed in this way. So the probability that zi equals ek, the marginal, it's the marginal distribution on zi that we care about. That's equal to the probability that zik, that the kth coordinate is 1, because the kth coordinate is 1 precisely when zi equals this kth standard basis vector. And that was just alpha k. Okay, I'm out of time in this video. Sorry, we'll have to stop once again, and we'll finish this next time. Okay, see ya.